Hello everyone. In the earlier class, we saw some basic system properties. First property was dynamicity property, that is static or dynamic. Then time invariance property, or you can say shift invariance property. Then third we saw linearity property. Then linearity property tells us about that whether the system is linear if it satisfies the superposition principle. Okay. Then fourth property we saw, that is a causal or anti-causal system. So causal system is that system if its output depends upon the present and past input. Okay, and for non-causal system, if its output depends upon the future also, then we will call it as anti-causal or non-causal system. The next property was a stability property, that is the system is said to be a stable if for every bounded input it produces a bounded output. That means if you produce or if you give input as a bounded, that is a finite number, or input as a finite, then we will get the output also a finite. If it is not true, then we are calling the system as a non-stable system. Okay, then the stable system is also called as bounded input, bounded output stable system. Then the next property was invertibility property. So a system is said to be invertible if there is a unique output for every unique input. This is what we saw in the earlier classes. Okay, and for invertible system, there should be a system which is exist, that is inverse system should be exist over there. Okay, so that we will call it as invertible system. Fine. So now in today's class we will see some few examples based upon these properties. Now let us solve the problem of linearity, that is check whether the system is linear or not. Example number 1, y of t is equals to t into x of t. Okay, so we have to check whether the system is linear or not. When we call the system is linear, when it follows the superposition principle. Okay, so what is superposition principle? That is, we have to make this system as two systems. Okay, that is x1 of t and x2 of t. Let us say y1 of t is equals to x1 of t. Okay, transformation on x1 of t, okay, which is nothing but t times x1 of t. Y2 of t, what is y2 of t? This is nothing but transformation of x2 of t, which is equals to t times x2 of t. Now we have to combine, now we have to combine the response. We have to combine the response. What we have seen earlier, this is the individual responses of the system. That is y1 of t and y2 t of the are the individual responses of the system. So y3 of t is nothing but the combination of a1 y1 t plus a2 y2 t, a2 y2 t. Okay, so this is nothing but your additivity property and the homogeneity property, or you can say a scaling property. Okay, so two systems can be additive, or you can say this a1 is multiplied by to y1. This is nothing but your scaling properties. Okay, so y3 of t is nothing but a1 y1 t plus a2 y2 t. Now if we put the value, then we will get a1 t times x1 of t plus a2, what is y2? That is t times x2 of t. Okay, so this is the first part we have seen. Okay, first part we have seen. Now if suppose we have x3 of t, or you can say transformation on x3 of t, which will gives us y3 of t, or you can say y3 dash of t. Okay, so now we have applied transformation on x3 of t, and what is x3 of t? X3 of t is nothing but the combination of a1 x1 t plus a2 x2 t. Okay, and on that we have applied transformation. Okay, and that is equals to t times, okay, t times
a1 x1 t plus a2 x2 t, right? And which is nothing but y3 of t. So this implies y3 of t is equals to y3 dash of t. This implies the system is linear system. Okay, so this implies the system is a linear system. So we'll see the steps again. Okay, so linearity principle says that when we have a system with a response y1 of t is equals to x1 of t, okay, and y2 of t is equals to x2 of t, okay, then if we combine these responses, this is that is nothing but a1 y1 of t plus a2 y2 of t, which is equals to the linear combination. This is the linear combination of two responses is equals to the response of that system. That is, this is your y3 of t. We have applied a response to a system. So if you not understand, if you not understood, I will explain it in another way in the graphical manner so that you will be better understand. Okay, for example, we have this is x1 of t. Okay, and then we are providing multiplied this as a1. Okay, this is your arbitrary constant. Okay, and then another x2 of t we have. Okay, and then this x2 of t is again multiplied by a2. Okay, so this arrow represents the multiplication. Okay, so a1t x1t plus a2 x2t, and then after that if we sum up this, okay, this is the summation. Okay, this is summation equation. Fine, I will redraw it. Okay, this is round, and then this is plus. Okay, now if whatever the addition is there, that is your summation of a1 x1t plus a2 x2t, this is your a2 x2t, and when we pass this, okay, this a2, when we pass this to the system, when we pass this to the system, this is your system, and then we will get y3 of dash. Okay, that is nothing but a1 x1t plus a2 x2t. This is one of the system. Okay, now in another system, that is when we have this is our x1 of t, when we pass this x1 of t to a system, okay, so this is my system. So what I will get, I will get, okay, this is the multiplication with a1, multiplication with a1, and then this is my x2 of t. This is again passed with another system, and then it is multiplied by a2 of t, and then later on if we sum up this, okay, if we sum up this and then we calculate the response, and that response is your y3 of t. Okay, y3 of t, and that is equals to a1 y1t plus a2 y2t. See here. Okay, so x1t is passed to the system. Okay, so it will gives you y1 of t here, and then that y1 of t is multiplied by a1. Okay, so at this point whatever the signal is there, that is a1 y1 of t, and at this point when x2 of t passed to the system, this is input to the system x2 of t, it is passed to the system. At this point the signal is y2 of t, and then it will be later on multiplied by a2 of t. To at this point it is a2 y2 of t. When we add these two signals, we'll get y3 of t, which is equals to a1 y1 t plus a2 y2 t. Okay, so this is what the homogeneity principle. Let us take another example. Let us take another example. Example number 2. So it is like y2 of t, sorry, y of t is equals to x square t. Y of t is equals to x square t, and we have to check whether the system, this is system is linear or non-linear, linear or non-linear. Okay, so again we have to we have to see this sequence for two you can say input signals, that is x1t and x2t. So when we apply transformation on your x1 of t, okay, y1 of t will find the transformation on x1 of t, and that is equals to your x1 square of t. Okay, x1 square of t. Now y2 of t is nothing but the transformation applied on x2 of t, that is equals to x2 square t. Okay, now what is y3 of t? Y3 of t is nothing but the transformation, or you can say combination of a1 x1 t plus a2 plus a2 x2 t. Okay, this is the generalized term. Okay, so now that is nothing but a1 x1 square. Okay, x1 square t plus a2 x2 square t. Okay, this is what one of the response you can say. Now we got y3 of t. So y3 of t is nothing but a1 x1 square t plus a2 x2 square t. Now let us find the response of the system. Now let us find the response of the system to linear combination of input. Okay, so that is nothing but when we apply transformation on x3 of t, transformation on x3 of t, which is nothing but y3 dash of t. Okay, so which is equals to transformation. Okay, transformation means we have to make as a1 x1 t, transformation on a1 x1 t plus a2 x2 t and its whole square. Okay, so that is nothing but a1 x1 t plus a2 a1 x1 t. Okay, a1 square x1 square t plus a2 square x2 square t plus twice of a1 a2 x1 t into x2 of t. This is your y3 dash of t. So y3 dash of t, which is not equals to y3 of t. What is y3 of t? Y3 of t is nothing but a1 x1 square plus a2 x2 square, whereas y3 dash of t is nothing but a1 square x1 square t plus a2 square x2 square t plus twice a1 a2 x1 t plus x1 t into x2 of t, and which is not equal to y3 of t. This implies the system is non-linear. This implies the system is non-linear. Okay, so the first example we saw where we got the system is linear system. We got the system is linear system because this is y3 of t is equals to y3 dash of t. Okay, that means it is when we combine two inputs, then its linear combination, or you can say a combined transformation on that signal will be equals. When this is true, then we will call it as a linear system. If it is not true, that is in the second case we have seen, so we are calling it as non-linear system. Then we are calling it as non-linear system. Okay, now let us consider y of n is equals to 2 times x of n plus 3. Okay, by looking at this, you can say that the system is not linear. The system is not linear system. Okay, because when you calculate its linearity principle, or you can say its superposition principle, you will find that the system is non-linear. I will tell you in another way. Okay, so we have some you can say postulates of linearity principle, or you can say the system is said to be linear. Okay, if it satisfies the superposition principle. Okay, another way, if it is satisfies the property of additivity, so it must satisfy the property of additivity. So it must satisfy the property of additivity. Property of additivity. Okay, so what is this meaning additivity? If we consider that x1 of n is equals to 2, and then x2 of n is equals to 3. From this example, x1 of n is equals to 2 and x2 of n is equals to 3, then if we know that transformation of x1 of n gives me y1 of n, okay, and which is equals to 2 times, okay, 2 times x1 of n plus 3, 2 times x1 of n plus 3. But what is x1 of n? That is nothing but 2 into 2 plus 3, and which is equals to 7. Fine. And then transformation of x2 of n, which is equals to y2 of n, which is nothing but 2 times x2 of n plus 3. But what is x2 of n? Which is nothing but 3 plus 2 into 3 plus 3, which is equals to 9. Okay, so we got y1 of n is equals to 7 and y2 of n is equals to 9. Fine. Now, now we know that y1 of n, y3 of n is equals to y1 of a1 of into y1n plus a2 into y2 of n. Okay, consider a1 is equals to a2 is equals to 1. So y3 of n is nothing but y1 of n plus y2 of n, which is equals to this is your 9 plus 7, so which is equals to 7 plus 9, that is equals to 16. So this is your y3 of n. Now y3 dash of n, y3 dash of n is nothing but a combination, you can say linear combination of 2 times x1 of n plus x2 of n plus 3. Okay, and we, now that is equals to 2 times what is x1 of n? So x1 of n is nothing but 2 and x2 of n is equals to 3. So 2 times 2 plus 3 plus 3. Okay, so 5 into 2, 10, and 10 is equals to 13, which is equals to 13. So y3 dash of n, y3 dash of n is equals to 13, and which is not equals to, we can say 16. Okay, because we got y3 of n is equals to 16. So y3 of n is not equals to y3 dash of n. This implies the system is non-linear. Okay, system is non-linear. Okay, so we have seen the additivity property. Okay, so the system should follow the additivity property, then and then only we are saying that the system is linear. If it is does not follow the additivity property, then we are telling that the system is non-linear. Another way is also there. Okay, which is very simpler way. Okay, so second way is nothing but if you provide a zero input to the system. Okay, if we provide zero input to the system, okay, then zero input instead of writing a 0 input gives 0 output. If we provide a 0 input to a system, then it will gives you a 0 output. Okay, so I will write again y of n is equals to 2 times x of n plus 3. Now, now if we if we calculate if we calculate or you can say assume if we calculate or assume the system at n is equals to 0, or you can say system at n is equals to 0, it has value 0, or you can say uh, at 0th input, or you can say y0 of n is nothing but 2 into 0 plus 3, which is equals to 3. Okay, so if we provide 0 at the input, so x of n is equals to 0 at particular time instance n0. Okay, so at particular time instant n0, so it will give me y0, which is equals to 2 times, or x of n is equals to 0. So we have provided input as a 0. This implies we provided input, that is our x of n is equals to input, and input is equals to 0. If we provide 0 input, it must give 0 output. If it is satisfied, then it will be equals to linear system. If it does not satisfy it, we are calling it as non-linear system. Because now in this case we have given a 0 as input, so we'll get the value 3. Okay, and this implies that the system is non-linear. Okay, so we have given input, or you can say 0, which is equals to x of 0, or you can say x of n. Okay, x of n is equals to 0 at particular instance. Okay, that is n is equals to 0. So y0 we have calculated, and which is equals to 3. Y0 of n is which is equals to 3. So we are calling the system is a non-linear system. Let us take another one example. So y of n is equals to x of n square. Y of n is equals to x of n square. So y1 of n is nothing but transformation on x1 of n square. Y2 of n is nothing but transformation of x2 of n square. Okay. Y3 of n is equals to a1 x1 n plus a2 x2 of n, or you can say a1 y1. Okay, y1 of n, I will rewrite this. Okay, instead of x1, actually it's not x1, it's a1 y1 of n plus a2 y2 of n. Okay, so which is nothing but a1 into transformation applied on x1 of n, you can say square, okay, plus a2 x2 of n square, which is nothing but a1 x1 square x1 n square plus a2 x2 n square. This is what your y3 of n. Now what is y dash of n? Y3 dash of n. Y3 dash of n is nothing but transformation on a1 x1 n plus a2 x2 n. Okay, so combine. Okay, so which is nothing but a1 x1 n square plus a2 x2 n square, and which is equals to y3 of n. So this implies the system is a2 x2 of n, okay, and this is equals to y3 of n. This implies the system is linear system, and the system is linear system. Now another example we will take. Yes, which is nothing but causality. Yes, we'll take the example of time invariant system. So based on shift invariance property, invariance property. So y of t is equals to sine of x of t. Y of t is equals to sine of x of t. So check the system for shift invariance, or whether the system is time variant or time invariant. Time variant or time invariant. Time variant or time invariant. So what are the steps for this? What are the steps for this? The first step is we have to shift the input, okay, or you can say shift the input by some time period, okay, or you can delay that input by time period. Let us say t1 time period, okay. So let us take first step. First step is to shift the time, or you can say time shift at input or delay. Time shift at input by t1. This also called as delay in delay in input by t1, and it can be represented as y of t comma t1, okay. So here we are delaying, so transformation on x of t minus t1. So just time shifted is there, or you can say it is time delay at the input, okay. So which is equals to t. Y of t is nothing but, sorry, sine of x into t minus t1. T minus t1. This is your y of t comma t1. Now then the second step, in the second step we have to delay the output, okay. So delay output by t1, and then check, okay, or you can say t minus t1, shift the output, delay, or you can say time shift the output. Y of t minus t1 is nothing but sine of x of t minus t1, sine of x of t minus t1. Now you can check y of t comma t1 is equals to y of t minus t1. This equation number 2 and equation number 1, okay. as 1 and 2. When we compare 1 and 2, we can see that y of t minus t1 is equals to y of t comma t1. That is when we shift the input by t, okay, and if we shift the output by t, then we'll get the same response. That is, time shift in the input result in the time shift in the output. Okay, this we have proved. So the system is called as time invariant. The system, we call it as time invariant. Next, let us take another example, second example, which is also we can say y of n in terms of discrete. Y of n is equals to n times x of n. Y of n. So first step is you can delay the input. So input is delayed. That means we can represent it as y of n comma, you can say n0, which is nothing but transformation of x of n minus n0. So input is delayed. So what is that? That is nothing but n times, okay, n times x of transformation on x times n comma n0, which is nothing but, so n times, so x times n minus n0. Okay, so this is your y of n comma n0. Now delay the output. So how do we delay? N minus n0, y of n minus n0 is nothing but wherever n is there, so you can represent it as n minus n0 into x of n minus n0, and which is not equals to y of n comma n0, which is not equals to y of n comma n0. So this is tell that this system is time varying system. The system is time varying system. Now let us take another example for causality, one or two examples for causality. So number one, the causal system or non-causal. Okay, for causal or non-causal. So y of n, first example, y of n is equals to x of minus n. Y of n is equals to x of minus n. So you can see that here. So why we are system is calling it as causal system? If the system is depends on present and past input, okay, then we are calling that system as a causal system. If the system depends upon the future input also, then we are calling it the system as non-causal system. Now put here, you can put here n is equals to, put n is equals to 0, so we'll get y of 0, which is equals to x of 0. Okay, put n is equals to 1, we'll get y of 1, which is nothing but x of minus 1. This is your, okay, this is your present. Okay, when n is equals to 0, we'll get the present input. At present output, we'll get the present input. Okay, sorry, at present input, we'll get the present output. Okay, at 0, we'll get 0. But what about this? At minus 1, that means at past input, we'll get a future output. This is also good. Okay, but what at when is equals to minus 2, we'll put, so we'll get y of minus 2, which is equals to x of plus 2, x of plus 2, which is nothing but the future input, which is nothing but the future input. So if the system depends, or if the system depends upon the future input also, then the system is called as non-causal system. Then the system is called as non-causal system. Understood? So take another example in terms of uh, continuous time domain. Y of t is nothing but x of 2t. y of t is nothing but x of 2t. Now, by looking at the system, we can say that the system is non-causal. Non-causal. Why? Because when we put t is equals to 1, so y of 1 is equals to x of 2. What is x of 2? X of t is nothing but the future input. This is your future input. This is your future input. So the system is non-causal. Let's take another example. Y of t is equals to x of t into cos of t plus 5. X of t into cos of t plus 5. Okay, this is causal system. Why causal system? Because at present input, okay, so output depends upon the present input. Okay, when whatever value of t you put here, so for example, if you put t is equals to 0, 1, 2 or minus 1, 2, you will get all the values of x of t. Okay, so I will rewrite it as y of 0, you will get x of 0 into cos of 0 plus 5. Y of 1 which is equals to x of 1 into cos of 1 plus 5. Okay, so you can see that at 0 input you will get 0 output. At present input you will get this output is also depends upon the present input, and it does not depends upon the future input. Okay, so the system is causal system. Causal system. So a system is said to be a causal system if it's depend on the present and past input only and not on the future input. For non-causal, it depends on future input also. It depends on future input also. Let us take another example so that you will again understand this. So y of t is nothing but integration from minus infinity to t x of t dt. X of t dt. So you can say that output here that depends on past. This is integration from minus infinity, that means past of t up to t. Up to t is there, that's why past and present. So the system is causal system. So the system is causal system. Let us take another example. dy by dt dy by dt plus y of t. Okay, this dy by dt is also y of t plus 2 which is equals to x of t. This is also, you can say, a causal system, because you can say that output, this dy by dt or y of t depends upon the present input only. Okay, so you can say that this is a causal system. Another example, y of n is equals to x of n plus x of n minus 5 plus x of n minus 7. So this system is also causal because it depends upon the present input. Okay, so it depends on the present input, and these are the past input. These are the past input. So the system is called as causal system. Now let us take another problem. Okay, let us go for the stability criteria. Stability, whether the system is stable or not. Check whether the system are stable or not. Stable or not. So y of t is equals to t times x of t. So why the system is called a stable system? Because if bounded input, if we give a bounded input, it should produce a bounded output. Then the system is called as stable system. You can see that here t, as t tends to infinity, your output, your y of t, because it is multiplied by t into x of t. If t tends to infinity, y of t tends to infinity. Okay, and that's why that's why it produces unbounded, or you can say infinite output. Okay, so the system is unbounded, so the system is not stable. The system is not stable. Second example, x of t into sine 50 pi t. X of t into sine 50 pi t. Let us say x of t is bounded. Let us say x of t is bounded. Okay, and you know that this term, that is sine of 50 pi t, sine of 50 pi t is between plus 1 to minus 1, because this is sinusoidal function and it rotates from plus 1 to minus 1. Okay, this is plus 1 and this is minus 1. So, and then it is multiplied by x of t, and we consider that x of t as bounded system. So this implies y of t is also bounded. Y of t is also bounded. So this implies the system is stable system. The system is stable system. Next example, y of n is equals to x of n plus x of n minus 2 plus y of n minus 2. So you can see that if x of n is stable, if x of n is stable, okay, and this x of n and x of n minus 2, these two are the your present and past input. X of n minus 2 is your past input and x of n is your present input. Okay, so if x of n is, we can say, bounded, if x of n is bounded, if x of n is bounded, then then your x of n minus 2 is also bounded. Okay, it is another term, your y of n minus t. Y of n minus t is nothing but the past output. Okay, so if x of n is bounded, x of n minus 2 is bounded, this implies your y of n minus 2 is also bounded. Your past output is also bounded, and hence that implies your y of n is bounded. So the system is stable. So the system is stable. So the system is stable. Now let us take the few more for invertibility system. Invertible or non-invertible system. So y of t is nothing but 2 times x of t. So when we call the system as invertible system, if it produce unique output at every unique input, so the input is unique, it should produce unique output. Okay, so then we are calling it as the invertible system. And if the system is invertible, there should be you can say inverse system. There should be a inverse system. So in this example, this is example, y of t is nothing but 2 times x of t has been given, and for this system, the invert system is 1 by 2. The inverse system is 1 by 2. That means this is my system. So I am giving this input to the system. So this is my system. I am giving the input to the system, and at the output I will get 2 times x of t. Okay, and when I pass this 2 times x of t to the another system, okay, and then this system is provided me w of t, which is nothing but 1 by 2 times y of t, and which is nothing but x of t. Okay, so if I give an x of t as an input to the system, okay, and then I will get output, that is my y of t is nothing but 2 times x of t. And when I give this 2 times x of t to this inverse system, I will get w of t is nothing but 1 by 2 times y of t. If you put y of t value here, so you will get it is equals to x of t. Okay, so original signal, here we have obtained the original signal. Okay, so we are calling this system as invertible system. So you have to think for the its inverse. Okay, if you have to think for the inverse, let us take another example. If we have a signal that is y of t, y of t is nothing but x square. Now this is square is there. So what is the inverse system is there? So for inverse system, so this implies the inverse system w of t. Okay, this is one of the notation we have representing w of t is nothing but square root. We have to take square root of y of t. This is what your system. So now square root of x square of t, what is that? That is nothing but plus or minus x of t, plus or minus x of t. So this is not a unique. This is not unique. Whereas our unique system is x of t, that is positive x of t we have sent to this. Okay. So this is your my x of t unique, and then I am getting y of t is equals to x square of t. Okay, and then y of t x square, this is my first system. If I provide this to another system, or you can say inverse system, that means square root of y of t. Okay, and then it will provide me w of t is equals to square of y of t. But what is y of t? Y of t is nothing but x square. So this equals to x square of t, and this is equals to plus or minus x of t, plus or minus x of t. Fine. So this is not a unique, you can say not unique. This is not unique. So this implies the system is non-invertible. The system is non-invertible. I think that's all. We have took some few of one or two problems for all these properties. In the next class, we will take a few more problems on this system properties. Thank you.